JD Kilgallin, product owner, analytics and AI. I've been in a variety of engineering roles here at Keyfactor over nearly 10 years now. Most recently, I've been leading development of our new Command Risk Intelligence module, where we're offering some deeper insights about certificates under management in our PKI as a service and CLA, or Certificate Lifecycle Automation as a service environments. I also led our 2019 research initiative that led to our IEEE publication, Factoring RSA Keys in the IoT Era. And so today, I want to talk a little bit about the connections between those projects. And on the one hand, how we see risk intelligence as a natural way to mitigate and remediate this factoring vulnerability that we're looking at. And on the other hand, looking at the factoring vulnerability as kind of a premier flagship risk that we're able to look at with the risk intelligence module. So to set the stage, I want to talk through kind of a hypothetical commodity device that's going to connect to a vendor's cloud and then attempt to communicate securely using mutual TLS. We'll look at a way that a subtle but fatal flaw can kind of disrupt that process. And then we'll look at how we applied that to actually break hundreds of thousands of RSA keys, securing traffic on the public internet. And then finally, again, we'll tie this to the risk intelligence. And this is not a sales pitch by any means. This will look really at how we're integrating our research findings into the products for the purposes of kind of addressing these risks that we're looking at. So the hypothetical is this. You can buy a smart outlet today, just something you plug into your wall, plug your devices into it, and then you can power them on and off with an app on your smartphone. So let's say that a vendor comes along with just a really ultra low budget version of one of these. Maybe power companies start giving them away for free as a power saving measure. So we might have millions and millions of these devices coming online in the span of a few months or a year. And let's even say that at a high level, these do pay appropriate attention to security and kind of follow general best practice or recommendations. So this is going to use mutual TLS, client certificate authentication, and it's going to have a secure bootstrapping process where it gets that certificate beginning with on-device key generation. So it's going to generate a key on the device, use that to submit a CSR and get the signed certificate back. And this way, the private key never leaves the device, never gets transmitted along any wires. And so in principle, this should keep an attacker from being able to get the private key that's stored securely on this device. And so maybe that's all great. Again, this at a high level is what we would recommend as best practice for device security. But let's look a little bit more closely at this on-device key generation step. So we know RSA keys have some disadvantages over ECC, much larger keys for one, and then we know both of those are being supplanted by the new quantum safe algorithms. But today, RSA is still the most common key type. So if this is going to generate a key on the device, it's more likely than not going to generate an RSA key. And so the way that looks, this will be maybe a refresher if you're familiar with RSA. This will be a quick overview if not. But you generate two large prime numbers at random. And then both the RSA public key and private key are going to be derived from those prime numbers. So it's important that the numbers themselves stay secret. If somebody else gets these numbers, the private key is derived from them. They can rederive the private key and then impersonate this device or decrypt stored communications, so on. And so the way that the public key component is derived from these two prime numbers is very simple. We just multiply them together. So we have primes P and Q. P times Q, we're going to call the RSA key modulus. And we can embed that in the public key without worrying that, at least worrying unduly, that somebody can recover the original prime factors because this integer factoring problem is not something that a conventional computer is known to be able to solve. So quantum computer is able to factor these integers, and that's where it's breaking some of the security assumptions that we've relied on. But we can also look at cases where even a classical computer can kind of avoid needing to solve the integer factoring problem. And one of the ways that's kind of easiest to get around this is if you take one arbitrary number and you want to find its prime factors, for like 2048-bit RSA, these are very large numbers. If you generated these keys, generated these prime numbers uniformly at random, there's just so many prime numbers, you wouldn't really have a good way to brute force or guess what those original factors were. What a computer, even a classical computer, is very much able to do, even if it can't factor a single number in isolation, is if you give two numbers, it's very easy to find the shared factors. This is something Euclid, back in ancient Greece, had this algorithm for finding the greatest common divisor, or GCD. So this is the largest number that will evenly divide both of the inputs. Now, if we look at how this modulus is generated, each modulus only has two divisors, right? It's P is prime, Q is prime. Those are the two divisors. And so if we take two different keys that have one of those factors shared, so one key is P times Q, the other key is P times R, when we run this GCD algorithm, it's going to come up with P as the greatest common divisor. P is going to divide both of those keys, and that's actually going to let us rediscover all of the original factors and compromise both keys simultaneously. So again, either key might be relatively secure in isolation, but we have a situation where if we analyze them in conjunction, we're potentially able to get more info than we could with either key alone. So again, if these keys were really generated at random, we wouldn't expect this to ever work. There's just too many primes. Everybody would come up with unique primes. So we're looking really to see how good this randomness really is in the wild. And we know if it's not random enough, we can take a large data set of keys, and if you have a large number of keys, the number of pairs of those keys is even larger and grows more quickly than the number of keys. And so, this is kind of like, if you're familiar with the birthday paradox in combinatorics, a group of 23 people has better than even odds of two people having the same birthday. And you have kind of a similar collision issue here. So we'll work an example here real quick. So if we take 14 and 15 as our two moduli, this top example would be an example of two secure keys. So no factors in common. GCD of 14 and 15 is 1. Nothing larger than 1 that will evenly divide both 14 and 15. But if we look at 21 and 15 instead of 14, we can run this Euclidean algorithm, and we would find that 3 evenly divides 21. And we can check that. 21 divided by 3 is 7. So yeah, that evenly divides. 15 divided by 3 is 5. So again, that evenly divides. And just in the process of checking there, we have come up with the other numbers. So 21 divided by 3 is equal to 7. So then 7 times 3 is equal to 21. And we have those two prime factors. So just the fact that this 3 was a shared factor between those modulus values has let us come up with all of the factors of both keys. And so this attack has been explored for a while, 13 years or more. And so the first team wanted to look at, is this really practical? If we get a bunch of keys together, can we start finding pairs that have a factor shared and start compromising those? And the answer is yes. And then pretty quickly, optimizations started coming along. So the second team made the key observation that you don't really need to check each individual pair of keys at a time. If you have a key that shares a factor with another key in the set, it's also going to share a factor with the product of all of the other keys. And so what you can do is multiply all of your keys together and start doing GCD computations against that. Now, that's great. That reduces the number of computations. But now you're doing computations on very large numbers. So you think each one of these is a 2048-bit RSA key. You multiply them together, and you quickly get very large numbers. But then the same team explored some recursion, some unintuitive number theory related to modular arithmetic. And it turns out that you can pretty quickly bring down the size of the numbers that you have to work with. And this means that you can do an all pairs GCD computation in quite efficiently, sub-quadratic time. We started by checking each pair of keys. We've gotten more efficient than that. Part of the Henninger team then went on to do a follow-up a few years later, where they looked at scaling this up to run in a distributed model across a larger cluster. And they were able to scale that up and look at more keys, break more keys that way. We started looking at this in 2019 as maybe one of the higher impact activities we could do with some data we'd collected about certificates we had online. So we got about 75 million certificates, RSA certificates of our own. Got another 100 million from CT logs. And we thought this distributed model was kind of the highest scale that had been tested so far. But there's complexity there, which means development effort, which means cost. And so we kind of wanted to look at this and see, if we just treat this as a leak code problem, sort of, can we quickly get something together where we can go in Azure, get a high-performance series VM, turn all the specs to 11, and what would it take to just get something running there that could do this rather quickly? And it turns out that's mostly an exercise in managing peak memory demand, which comes at a specific well-known part of this computation. And we were able to make some optimizations that, let us run this with just about $3,000 of compute time in Azure. So really showed that the modern cloud computing made this attack more feasible. So then the next question is, where are these keys coming from, right? How are bad keys ending up, and who's generating them? So the 2012 team was able to identify some vendors associated with some of these compromised keys. And I'm going to show a table on the next slide. And I know some of these companies are represented here in our attendee base. But if you see your name, you'll also quickly see that you're in very good company. So the takeaway is that this is a systemic issue. Affects a large number of players. And we're not trying to call anybody out, right? And we also know this is from the 2012 publication. The 2016 team looked at following up with some of these companies, and some of them have responded to the researchers. Others, I'm sure, as just part of security modernization efforts, have maybe corrected some of these issues. But it's kind of a matter of whack-a-mole, right? Traditional QA processes aren't really going to tell you that if you generate millions of keys and somebody collects them and multiplies them all together, that it's going to cause a security problem for you. And of course, these smart outlet manufacturers, new product lines are coming all the time, dumping millions of keys that could be vulnerable to this. We also know that even if this is getting better at kind of a product design stage, the overall volume of certificates is increasing in a way that kind of counteracts that effect. So if we had 10% of 100 certs before, and now we have 1% of 1,000 certs, either way, we're coming up with certificates. We also have some findings that suggest that you can look at some very basic issues with a certificate and kind of judge how likely it is that it's going to have more serious exploitable vulnerabilities like this. And so, if this is a matter of collecting certificates from diverse data sources, kind of evaluating with some heuristics how likely they are to be vulnerable to these serious issues, and then doing analysis on that, that kind of pattern recognition problem is something that modern AI and machine learning techniques really kind of also serve to increase the concern that this attack might give someone. So, some parts have gotten better, other parts still remain a concern, and in some ways, this is more relevant today with these AI and machine learning techniques. Of course, RSA as a whole is under a lot of consideration for this post-quantum migration. So this really is still relevant today. But when we first looked at this in 2019, we knew we wanted to publish this in a proper peer-reviewed publication because it was really kind of uncanny how closely our research conclusions aligned with some of our marketing messaging. If the crypto agility folks say that crypto agility is good for you, we wanted to be able to back that up a little bit, right? So, we published this in the 2019 IEEE conference on trust, privacy, and security in intelligent systems and applications. Really to highlight the fact that your keys, that you believe are secure, that you rely on to secure your data, might have a latent defect that you could discover at any time that meant that it was not providing the security value that you thought. And the appropriate action would be to revoke and replace that certificate. So, we have, this is just one of many attacks that could lead to that kind of situation. So the takeaway really is not that you need to improve your random number generation, it's that you need to be prepared to replace these keys. So, one of the ways that we talk about command, I think some of you are customers, some of you might be less familiar. This is our certificate lifecycle management platform. And one of the ways that we talk about it is the crypto agility platform, because a lot of its features are oriented around helping organizations deploy these new keys at scale to their systems and devices that need new trusted credentials from their enterprise PKI. So I want to take the last part of this talk and go through some of the ways that we're taking these research findings and putting them in this new command risk intelligence module that we've just announced. So the first part is not terribly research oriented. This is really pretty basic. We can't tell you about risks with your certificates if we don't know about them, right? And sometimes the riskiest thing is just that a certificate is untracked. So we have discovery and inventory capabilities in the base product. With risk intelligence, we extend those. We look at certificate transparency logs, historical records of host scans, and certificates with subject information matching your domains, but hosted on some other domain. We pull all of these in just to ensure that we really have your full digital footprint under analysis. Then we take these certificates, along with any certificates that you already had under management, and we run each one of them through a series of checks that looks at kind of a different risk concept. So this factoring vulnerability is one of the things that we look at. Some of the checks are more mundane, checking CAB forum baseline requirements, number of letters in the country code field should always be 2. If you have 3, does that mean you're insecure? Probably not the same way that this factoring attack means you're insecure. But these are all rooted in X509, CAB forum, NIST standards, and our own research. And then after we implemented these checks and expanded inventory capabilities, we started looking at some statistics about this data, correlations between certificate subject and key attributes, as well as the individual risk factors or findings that we were coming up with. And we pretty quickly realized that this statistical information could be formulated into a predictive model that would kind of estimate the risk level that the certificate would be assigned. So we find direct risks here with these checks, but then just based on our research about how those risks present, we're seeing that a lot of times the most visible errors are not the most significant, but they're highly correlated with the significant issues. Basically a common cause that the key generation and certificate issuance process was not a robust, credible enterprise process carefully vetted by qualified PKI professionals. This was some PKI that somebody stood up, kind of fire and forget, and it started issuing certificates. So you can imagine that has both trivial but visible issues and serious issues, but those might take extensive cryptanalysis. If you wanted to look at those at scale, that would be more difficult. But with this predictive modeling, we can look at some of the more basic information and kind of gather how likely it is that that certificate has more serious issues. So this is where, again, we see contemporary AI and machine learning really able to effectively implement some heuristics that would help an attacker find plausible targets that are at increased risk. Then, okay, we do all of this, say we find issues with 10,000 certificates. Again, this goes from country code has the wrong number of letters up to key usage or basic constraints. Errors mean your whole PKI is compromised. So we take these findings or risk factors, we assign a weight to each one. So we kind of quantify how much risk that issue presents, and then we add those all up to make a certificate's overall risk score. And then the last thing is, again, we want to make sure that these issues, which might require that you revoke and replace your certificates, are all available within the CLM platform where you would perform those crypto agility operations. And so we take all of this info, the risk factors, findings, weights, overall score, and we use certificate metadata in command to make all of this information available through the existing command UI and API. So that ties into our query, collections, alerting, reporting, and automation capabilities. And so this just really kind of offers a significantly deeper level of insight for our PKI as a service and CLA as a service environments. So these are some of the risks that we're looking at. If you're interested in hearing more, I'll be over at the garage, and also happy to talk with anybody around the conference, or if you'd like to schedule additional time, happy to do that as well. Thank you.